Can the people on Zoom hear me?
Yes.
Thanks.
Okay, we'll go ahead and get started. So what we're going to do today is I'm going to review the answers for the last exam. And so if you have any questions or anything during that, please let me know. And just to remind everyone that the exam answers are posted on Canvas. So if you want to check something later, you can. It's up there. Then once we finish going over that last exam, then we'll start on chapter 19. So we're going to go back and do some additional thermodynamics this week. And so we'll do chapter 19 today, and we'll finish it up on Thursday. And then next Tuesday, so a week from today, you'll have a quiz, your fourth quiz, and that will cover chapter 19, this thermodynamic stuff we're talking about this week. Okay, so let's take a look at the exam. So the first question was, a Bronsted-Lowry base is defined as a substance that is what? And the Bronsted-Lowry base acts as a proton acceptor. So for Bronsted-Lowry, acids are protons donors, bases are proton acceptors. Number 2, the molar concentration of hydroxide ion in pure water is what? Well, the correct answer was 1 × 10⁻⁷. So you needed to remember that the hydrogen ion times the hydroxide ion equals 10⁻⁴ in water, and each is 10⁻⁷, because pure water is neutral. Number 3, you were given several acids and their pKa's, and you needed to identify the one that is the strongest acid. So the answer was HF, 6.8 × 10⁻⁴ was its Ka. And the way to think of this is acid dissociation constant, you have products over reactants, so that hydrogen ion concentration is in the numerator. So the bigger that number, the bigger the Ka. And so by looking at these Kas, you look for which number is the biggest, and that's the one associated with HF. Okay, number 4. We have an aqueous solution, and we're told that the pH is 7.46. And then we want to know, what is this mystery compound? And the answer is it's a weak base. So since the pH is above 7, then we know it's a base. And since it's around 7-ish, it's not a strong base. Strong base would maybe be 10 or 12, something like that. So the answer is weak base. Number 5, what is the pH of an aqueous solution that contains 1.35 × 10⁻⁸ molar hydroxide? So if we know the hydroxide concentration, we can find pOH from that. So minus the log of that value gives us a pOH of 7.87. And we know that pOH plus pH has to equal 14. So if we substitute in the pOH value into this, 14 equals pOH plus pH, then we can solve for pH, and then we know then it's 6.13. Number 6, once again, we have another aqueous solution, and we want to find the pH of it. And we're told it's 0.5 molar sodium hydroxide. So similar to the previous problem, we can go ahead and find the pOH by doing minus the log of that concentration, and that's 0.30. Using that 14 equals pOH plus pH relationship, we subtract 0.3 from 14 and get 13.70. So those two problems are pretty much the same problem. Okay, number 7. If HZ is a weak acid, an aqueous solution is prepared by dissolving 0.02 moles of HZ to yield 1 liter of solution. And then we're told that the pH of the solution is 4.93. And we want to know what the Ka is. So we can go ahead and write out that reaction. So it'd be Hz dissociates to H plus Z minus. And then we can use that Henderson-Hasselbalch equation. pH equals pKa plus log of, in this case, Z minus divided by Hz. And then we can look at our relationship and we see for every mole of H plus that we form, we're going to form 1 mole of Z minus. And we were told the pH of the solution being 4.93, so we can calculate the hydrogen ion concentration from there. So if we say pH equals 4.93, that would equal minus the log of the hydrogen ion concentration. And so we raise 10 to the minus 4.93, and we solve for that, and we get 1.17 times 10 to the minus 5 molar. As I said, from the Hz going to H plus Z minus, our chemical reaction equation, we know that for every mole of hydrogen ion, we have a mole of Z minus. So now we know Z minus concentration, we know Hz concentration, and we know the pH. So we can plug those values into our Henderson-Hasselbalch equation and get 4.93 equals pKa plus the log of 1.17 times 10 to the minus 5th divided by 0.02. So for these types of equations, then we go ahead and then solve for pKa, and we get a value of 8.16. We're not quite finished yet because we wanted Ka, so we have to take the antilog of that, and that gives us 6.9 times 10 to the minus 9. Okay, number 8. In number 8, we're told that the acid dissociation constant of acetic acid is 1.8 times 10 to the minus 5. And we want to know what is the pH of an aqueous solution that has 0.1 molar acetic acid in it. So we can write out our acid dissociation reaction equation. Acetic acid going to H plus acetate ion. In these types of things, we neglect that loss of 0.1 minus some value X. We neglect that X because we know from the pKa that it's a weak acid, so there's not much of that occurs relative to the 0.1 value. So that leaves us with 0.1 molar acetic acid, HAC, and then X and X of the hydrogen ion concentration in the acetate. We have our equilibrium expression. Acid dissociation constant equals H plus concentration times acetate concentration divided by acetic acid concentration. We go ahead and fill in our values, X for both hydrogen ion and acetate ion, because that's a 1-to-1 molar relationship, and then 0.1 molar in the denominator for the acetic acid, and then solve for X. The value that we get for X is 1.34 times 10 to the minus 3. That's the hydrogen ion concentration. And then if we do minus the log of that to get the pH, we get 2.87 is our answer. Number 9, the base dissociation constant is given to us as 1.4 times 10 to the minus 9. And then we want to find the acid dissociation constant for the conjugate ion. So here you needed to remember that Ka times Kb equals 1 times 10 to the minus 14. So if you remember that, then you could just plug in your Kb value for that and solve for Ka. And you'd get a value of 7.1 times 10 to the minus 6. Number 10, which solution has the highest concentration of hydronium ions? So hydronium ions is the same as hydrogen ions. And so basically it's asking which is the lowest pH. And so the lowest pH in these choices is 3.0. So that low pH, that's the most acidic hydrogen, highest hydrogen or hydronium ion concentration. Number 11, hydrochloric acid is a strong acid. What does this mean? Well, definition of a strong acid is that it completely dissociates, kind of similar to a strong electrolyte, it completely dissociates. So the correct answer was it dissociates completely to H plus and Cl minus when dissolved in water. Okay, number 12. Number 12, which of the following expressions is the correct equilibrium constant expression for this reaction that's given? So the reaction was HF plus H2O going to H3O plus and F minus. The thing you had to note there was that the water has a little L in parentheses next to it. That tells us that that's a pure liquid, and pure liquids count as one and don't show up in our equilibrium expressions. So then we wouldn't use that one, but we'd use the other three components of this reaction. And we'd have products over reactants. So products would be concentration of H3O plus times the concentration of F minus, that divided by the concentration of HF. We'd go back and look to see if there's any coefficients in front in our reaction equation, and there's not. So we're good to go there with just H3O plus times F minus divided by HF. Okay, 13. So for 13, we're given a reaction H2 plus I2 going to 2 moles of HI. And we're told that the equilibrium constant is 50 for this. And then we're asked a question as to what do we have going on at equilibrium? Well, remember, it's products over reactants is how we calculate the equilibrium constant. So the HI concentration is in the numerator, and then the H2 and I2 concentrations are in the denominator. So for that equilibrium constant to be greater than 1, then we have to have a lot of product, right? If we have a lot of reactants, it'll be less than 1. So the answer to this is products predominate. 50 is a pretty good size number, well above 1. So you have a predominance of the HI. Number 14, which of the following could be added to a solution of acetic acid to prepare a buffer? Well, we talked about when we're preparing buffers of these weak acids, there's 2 ways we could do it. One is we can add the conjugate base. So in this case, we could add something like sodium acetate to it. Or we could add a strong base. And then the strong base will neutralize some of the acetic acid and then have you have the acetate ion, which is what you want to have. So the correct answer for this is sodium acetate or sodium hydroxide. Number 15, calculate the pH of a solution prepared by dissolving 0.150 moles of benzoic acid in 0.3 moles of sodium benzoate in water to yield a 1 liter solution. And then we're given that the Ka of benzoic acid is 6.30 times 10 to the minus 5. So if we write out that dissociation of benzoic acid, so benzoic acid dissociates to hydrogen ions and benzoate ions. And so the key there is the coefficients are all 1. And then we can write an equilibrium expression as well. But because this is a weak acid, we can go ahead and use the Henderson-Hasselbeck equation. So pH equals pKa plus the log of benzoate divided by the concentration of benzoic acid. So we were given the benzoic acid values, we were given the benzoate values, so we can plug those in. And we were given a Ka value. If we have a Ka value, we can do minus the log of that to get pKa. So now we have a pKa value, we have those two concentrations, and so we can set up our math and then go ahead and solve for pH, which is 4.50. Number 16, the pH of a solution prepared by mixing 40 mils of 0.125 molar magnesium hydroxide and 150 mils of 0.125 molar HCl. So, well, whenever we have a problem like this, one thing we want to do is get everything into moles. So we have a volume of our magnesium hydroxide and we have a volume of our HCl. So we can go ahead and convert that mils and use our molarity to find how many moles of each of those we have. So we have 40 mils, which is 0.040 liters times the 0.125. And that tells us we have 5 times 10 to the minus 3 moles of magnesium hydroxide. Well, the key thing here is that's moles of magnesium hydroxide. We know that we get 2 moles of hydroxide for every mole of magnesium hydroxide. So to get the moles of hydroxide, we multiply that by 2. And so it'd be 10 times 10 to the minus 3 moles of OH minus. To get the moles of acid, 0.150 liters. That's converting that 150 mils to liters. And then that times 0.125 tells us we have 1.875 times 10 to the minus 2 moles of HCl. So then we can simply subtract the moles of hydroxide from the moles of hydrogen ion, and tells us that we have 8.75 times 10 to the minus 3 moles of hydrogen ion left. And then we want to divide that into 1 molar value. We want to divide that by the total volume. We had 40 mils and 150 mils. We need to work in liters because we want moles per liter. So then it's that number of moles divided by 0.040 plus 0.150 to get total liters. And that comes out to 0.04605 molar. Still not done yet because we wanted it expressed in pH. So we do minus the log of that. And we get a value of 1.34. Number 17, determine the KSP for magnesium hydroxide, where the solubility is 1.4 times 10 to the minus 4 molar. So we write our expression for that. So we have the magnesium hydroxide going to magnesium plus 2, and then 2 moles of hydroxide. So we kind of knew that already from the previous problem. Then we can do our KSP expression. So KSP is equal to X representing the magnesium plus 2, and then 2X, which represents the OH concentration. And then because the coefficients in our balanced equation have a 2 in front of the hydroxide, we have to square that value, that concentration. And so then if we plug all those in, we get 1.4 times 10 to the minus 4. And then that's times the quantity of 2 times 1 to the minus 4th, that whole quantity squared equals our KSP value. If we then solve the math, we get 1.10 times 10 to the minus 11. Okay, number 18. Calculate the percent ionization of formic acid in a solution that's 0.322 molar in formic acid and 0.178 molar in sodium formate. And we're given the Ka rather for formic acid. And that's 1.77 times 10 to the minus 4. Another opportunity to use the Henderson-Hasselbeck equation. So we're given the Ka, so if we do minus the log of that, we get the pKa, that's 3.75. We have concentrations for formic acid and formate, so we can fill those into that log term. So it gives us log of 0.178 divided by 0.322. We go ahead and solve all that, and we get a pH value of 3.49. We know from the stoichiometry that, or rather, we know from the pH that we can then take the antilog of that and get a hydrogen ion concentration. That's 3.2 times 10 to the minus 4. Well, we wanted it to be percent ionization of the formic acid. So now if we have 3.24 times 10 to the minus 4 is our hydrogen ion concentration. We divide that by what we started with in terms of the concentration of the acid, which was 0.322. And since we want it expressed as a percentage, we have to multiply that ratio by 100. And if we do that, we get 0.101%. So personally, I thought that was one of the more difficult problems on the test, but in general, people did pretty well on that. So good job. That was nice to see. Number 19, 25 mils sample of HCl is titrated with 0.139 molar in AOH. And then the equivalence point, we're told, is reached at 15.4 mils of base. And we want to know what that concentration of HCl was. So we have a strong base, strong acid titration. And so what that means is that at our equivalence point, we've neutralized, in this case, we've neutralized the HCl. So what we're going to do is we're going to take that volume of base, the 15.4 mils, convert it to liters, and then multiply it by our molar concentration of sodium hydroxide to find out how many moles of the base were used. If we do that, we find that it's 2.14 times 10 to the minus 3 moles of sodium hydroxide. If that's the moles of sodium hydroxide that were used, we know in this titration it's a 1-to-1 molar reaction because it's a strong base, strong acid. And so if that's the amount of base that was used, that tells us that's the amount of moles of H plus of acid that are there. So we started out with 25 mils of the HCl. So this number of moles, the 2.14 times 10 to the minus 3, that represents the number of moles of acid that must be present. So to get the concentration, we take that mole value and divide it by the volume of acid that we were working with. And as I said, in this case, it's 25 mils. We need to convert that to liters to have moles per liter. And we wind up with 0.0856 moles per liter of HCl. So it was kind of interesting because, like I said, I thought 18 was a little more difficult problem than 19. People did pretty well on 18. There were more problems getting 19 right than 18. So that was a little disappointing. I would suggest if you got number 19 wrong, go back and take a look at it again, because we've talked about that in class, and I know you've done a similar calculation in lab. And so my hope is that if you're still a little confused by it, take a look at it again. If you have any questions, let me know, or let your lab instructor know, because there's a good chance you might see something like that again, either in the class final or the lab final. All right, number 20, the last one. What's the molar solubility of silver carbonate, Ag2CO3 in water? And you're given a KSP value for it. So the first thing you wanted to do was write out that solubility product reaction and balance it. So silver carbonate goes to silver ions and carbonate ions. To get it to balance, you had to put a 2 in front of the silver. So you have that 2 coefficient there. and then that impacts what your KSP expression is going to be. Because KSP, remember, is silver ion concentration squared because of that coefficient of 2, and then carbonate concentration. Because 2 moles of silver are formed for every mole of carbonate, then when we fill in our variables, we get 2x, that quantity squared, times x equals our KSP value, which was 8.1 times 10 to the minus 12. Then you wind up with 4x cubed equals 8.1 times 10 to the minus 12. And finally, 8 cubed equals 2.025 times 10 to the minus 12. This was your chance to show off your calculator skills, finding the cube root, and we talked about that. So I was pleased to see most people were able to do that. So once again, if you weren't, just go back and take a look at your calculator maybe and make sure you can do this. And if you did that correctly, you got 1.3 times 10 to the minus 4. So that's it for reviewing the exam. Any questions about any of the problems on there? Just to remind everyone, it is on Canvas. The answers are posted on Canvas. So if you want to take a look at it a little more closely or rework a problem or something, you can do that. But if there's no questions, then I'm going to go ahead and bring up chapter 19, and we'll start talking about some more thermodynamics. Okay, hopefully everyone can see the slide. And we're going back to thermodynamics. So if you recall, we talked about thermodynamics last semester. We started talking a little bit about it. We talked about the first law of thermodynamics. And now what we're going to do is we're going to refresh ourselves a little bit on that first law, but then we're also going to start talking about the second and third laws today and on Thursday. So in the past, we said that energy cannot be created or destroyed. And because of that, the total energy of the universe is a constant. And that was our first law of thermodynamics. And remember when we talked about energy, we said it can be with the system, it can be with the surroundings, so you can move it around. It can take different forms. But you can't create it, you can't destroy it. So first law of thermodynamics, basically total energy is constant, but it can be converted from one form to another, and it can be transferred between the system and the surroundings. Okay, so it can kind of go back and forth. So we can move it around, we can change its form, but we can't make it, we can't destroy it. First law of thermodynamics. And remember, that's where a lot of this, when we talked about this before, centered around heat and delta H and enthalpy and all that. So we're going to bring back enthalpy. That was the delta H, if you recall. We have different types of delta H values, but in general, delta H was enthalpy. And that had to do with transfer of heat. So heat absorbed by a system, things like that. And so that's still important, that movement of energy, movement of heat, transfer of heat is still important. But now we're going to talk about another term called entropy. And we mentioned this a little bit in the past, so we'll go over it again. In entropy, the way I think of it is it's randomness, it's chaos. And so, and when we talk about measuring entropy, we're talking about measuring that randomness in a system. And we're going to introduce a term here called spontaneous reactions or spontaneous processes. And enthalpy and entropy, so that movement of heat, that movement of energy, and then the randomness associated with the system, both of those play a role in determining if something is spontaneous or not. And you'll see we're calling them processes because it does apply to chemical reactions, but it also just applies to things in general. And so that's why we'll tend to use the word process most of the time. When we say a process is spontaneous, what we're saying is that it happens without any outside influence or assistance, however you want to think about it. And so the example that we have here on these two pictures on the right-hand side of the slide is we have a person who's holding 2 eggs up over a table, and then they let go of the eggs and the eggs fall to the ground or fall to the table, and in this case, they break. So that process of holding something up, whether it's eggs or something else, and letting go of it, you don't really do anything. It just happens. It's spontaneous. And so processes there's a few things about spontaneous processes. Processes that are spontaneous are only spontaneous in one direction. So in this case, the person has the eggs up in the air, lets go of them, they fall down to the surface. That happens. They can hold their hand up over those eggs as long as they want, but the eggs aren't suddenly going to come back up into their hand. All right. And so since they are spontaneous just in that one direction, they're spontaneous just in that one direction because the only way to get them to come back up would be to do something. You know, we could scrape them up off the table here and put them back up in that person's hand, but that wouldn't be spontaneous. We'd have to put energy into it, put work into it to get it to move back up. So spontaneous processes are similar to this, where the direction that they're spontaneous, it just happens, but to come back the other way, you can wait, but it's nothing's going to happen unless you put something into it. A couple things about these. Spontaneous processes are often fast, like dropping those eggs, that happens pretty quick. But they don't have to be fast. There are examples of slow spontaneous reactions. The one I always think about is when you see metal rusting. That's a pretty slow process, right? But yet that's a spontaneous reaction, spontaneous process. Another thing is, don't think that something that's non-spontaneous is impossible. So the egg example, probably not the greatest one because the eggs broke when they hit the surface. But let's say instead of an egg, it was a brick that you had in your hand and you let go of it. Well, you let go of that brick and it hit the surface, that would be spontaneous. You didn't really do anything, you just let go of it and then it fell down. The brick's not going to come back up into your hand because that's non-spontaneous, but say that table has some kind of lift under it. Well, you could press a button and the table starts rising and the brick would come back up into your hand and you would have it. So you could make it go back up, but you'd have to put work or energy into it to make that happen. So non-spontaneous doesn't mean impossible. It just means it's not going to happen on its own. And that's the way to think of it. So once again, spontaneous processes, the easiest way to think of it is just stuff that happens on its own. Non-spontaneous means it's not going to happen on its own unless there's some type of interference, so to speak. There are some factors that can determine whether a process is going to be spontaneous or not. And two of them that do affect are temperature and pressure. These can affect spontaneity. And so let's take a look at an example here where we have some water in some Erlenmeyer flasks. And let's take a look here at how temperature affects the spontaneity of what the water does. So in the Erlenmeyer flask on the left, we have water in there, and we can see it's kind of hard to tell on the slide, but you can see it looks like it's frozen there. And then on the right-hand side, once again, we have another Erlenmeyer flask. It's about the same amount of water, and in that case, it's in its liquid form. Well, on the left-hand side, where we have the flask full of ice, if we increase the temperature so that it's above the freezing point of water, which is 0 degrees C, if we increase that temperature, then that ice is going to start to melt and go from solid to liquid. And that's a spontaneous process. On the right-hand side, with the water that's already in liquid form, if we drop the temperature below the freezing point, so if we drop the temperature to less than 0 degrees C, then that liquid water is spontaneously going to start to freeze and become solid. So here's a case of where you have water in an Erlenmeyer flask, and depending upon what the temperature is, you may or may not have a spontaneous process occurring. So that's an example of where the temperature of what you're working with determines whether it's spontaneous or not. You have similar issues with gases in terms of what the pressure is. That can help determine if it's going to be spontaneous or not. So kind of along the line of the same thinking is there's reversible and irreversible processes. And so let's talk about a reversible process first. So in a reversible process, the system changes so that the system and surroundings can be returned to the original state by basically reversing the process. Okay, and so what you're saying is that the reverse direction, whenever an infinitesimal change is made in some property of the system. And so let's take a look at the examples that we have on this slide at the top in the figures. So on the one on the left, we have the system in the middle, and then we have the surroundings around it. So the system in the middle is the kind of the darker red portion. And we're saying that if that temperature in the system is increased by some small amount, what happens? Well, if that system temperature in the middle is increased, then what will happen is the surroundings will try and take up that extra energy to balance things out. So what happens is to keep the overall system and surroundings the same, the system gets increased. We want to lower that temperature, so we do that by the surroundings taking up some of the heat to balance it out. On the right-hand side, we have a similar thing, except in this case, the system, which is in the middle, this kind of lightish pink color, that is the temperature has been lowered a little bit of the system. So now that system is temperature is a little bit too low. To get it back into balance, there'll be a small amount of energy, small amount of heat that transfers from the surroundings into the system. So when we have these reversible processes, what we're really saying is that the system and surroundings, that it's a slight enough shift that they can manage that themselves. In kind of a way, it's kind of like the buffer systems we were talking about in the last chapter, couple of chapters, that you can have a disruption, but you're able to kind of handle it. If we look at an irreversible process, that means that you can't get things back to how they were without putting some effort into it, doing some interference is the way I think of it. And here we have an example using some gases. So let's take a look at these three figures. So what we have on the left here is we have a container, and in the container on the far left, we have a piston. Then we have half of the container on the left of it that's been evacuated. So there's a vacuum there, there's nothing there, no gas. Then we have a partition between the half of the container that's been evacuated and the other half, this kind of grayish bluish part, that's a gas that's been introduced. So now we have this container. piston to the far left, an evacuated portion of the container, this kind of divider between the two sections of the vacuum and then where the gas is stored. And if we go ahead and then take this partition and lift it up and take it out of the container, well, now what we see is, we see that gas disperses throughout the whole container. So this gas expansion, that is going to happen as a spontaneous process. Remember we talked about the spontaneous process as the one that just happens. You don't have to do anything to it. And when we talked about gases in previous chapters, remember we said one thing about gases is you put them in a small container, they fill the whole container. You put them in a big container, they fill the whole container. So the gases are doing that here. That's a spontaneous process. We take that partition out. Now it's, the whole container is available to it, and it'll go ahead and distribute through that, expand through it. But we didn't have to do anything. We didn't have to do any work. It just happened. Well, if we wanted to get back to this situation that we have on the left, where we had half of a vacuum and half of the gas. In other words, if we wanted to get the gas back to just taking up half of that container, well, we could hope that it's a spontaneous, reversible process. And we could wait, and we could wait, and we could wait, and we'd still be waiting forever. It's not going to happen on its own. But just as we said before, that irreversible processes just means that they don't happen on their own. It doesn't mean you can't do it. And so in this case, we can do some work, and that's where you see on the right-hand side, this right-hand figure, where we see work, and what the work is pushing that piston. So we're putting some work on that piston, we're driving it, we're pushing it, and we can push it to the halfway mark just where that movable partition was. And now what we see is on the left-hand side, we have an evacuated portion, half evacuated. And on the right-hand side, we have all that gas compressed back again. So we've gotten back to where we were at the beginning, but we had to do work. Okay? And so in this case, it didn't happen on its own. We had to do work to get it back and compress that gas. So when we talk about reversible and irreversible processes, there's a couple things. Because real processes can only approximate the really small changes associated with reversible processes, all real processes are reversible. And that's good to remember, but the one I really want you to remember is that because spontaneous processes are real processes, all spontaneous processes are irreversible. Okay, so that's the key takeaway here. Spontaneous processes are irreversible. And what do we mean by irreversible? Think back to that egg example. You hold the egg up, you let go of it, it falls to the ground. That egg's not going to suddenly fly back up into your hand, okay? So that egg dropping is a spontaneous process, but it's not reversible, it's irreversible. And that's the key takeaway from this slide here. Okay, so let's shift gears a little bit and talk about entropy. Remember we said entropy is randomness, it's chaos, it's disorder. And so that's what we want to talk about, how we measure that and how that relates to these processes. So if you recall, we said previously that a state function is something that it doesn't matter how you got there. It just matters where you started and where you ended up. Okay, it's kind of like you're all here at Webster University, you come in as a freshman. Each of you is going to take different classes. Some of you may take, you know, more science classes, or you may switch to business, or you may do whatever. But if at the end of 4 years you have a degree, well, it doesn't really, you're not that concerned about the path. It's started as a freshman, 4 years later as a senior, I graduated, yippee, I have my college degree. So that would be a state function, and that's what entropy is also. When we talk about these state functions, we talk about change, so final minus initial, so the final entropy minus the initial entropy, that's represented by delta S. And so we can find out what delta S is by understanding the heat transfer from the surroundings at a particular temperature. And so remember when we talked about delta H values, Q was often the term we used for heat. So the Q reversible is the heat that would be transferred in the process if it were reversible. So we use those constants, which we can look up, and we can get that value divided by the T, the temperature, and that tells us what that change in entropy is. So that brings us to the second law of thermodynamics. And the second law of thermodynamics starts to help us understand what's going on with respect to entropy. And what the second law of thermodynamics tells us is that the entropy of the universe increases in any spontaneous process. And we've got some relationships here that we'll talk about. But first law of thermodynamics was, you know, energy heat isn't created or destroyed. It changes forms. It changes whether it's the system or the surroundings, but it doesn't get more or doesn't get less. It's a constant. Second law tells us that the entropy of the universe increases in any spontaneous process. There's two relationships that we can talk about. One is reversible process. So for a reversible process, the delta S of the universe, so the entropy of the universe, is equal to the delta S of the system plus the delta S of the surroundings. So the change of the system plus the change of the surroundings. And that's going to be equal to 0. And that's think back to when we were talking about, you know, that reversible process where the system gained a little bit of heat, for instance, and then the environment would balance it out. That's kind of what we're talking about there. So reversible processes, the delta S for the universe, the sum of the system and surroundings will be 0. So they'll even out. In irreversible processes, the delta S of the system plus the delta S of the surroundings is greater than 0. So in other words, our delta S of the universe is positive. Well, that's what we set up here in this first bullet point. Entropy of the universe increases in a spontaneous process. Spontaneous processes are irreversible, right? So earlier we defined spontaneous process as being irreversible. So that means if we're going to obey the second law of thermodynamics, that chaos has to increase in the universe. And that's what this second equation is telling us. System plus surroundings, if that's greater than 0, irreversible process obeys second law of thermodynamics. So let's take a look at entropy on a molecular scale. We're headed towards a this area of study called thermodynamics. And thermodynamics is more studying this on a more macro type scale. But to get there, first we need to talk a little bit about what it is on the molecular scale. And so here we have a figure at the top, and let's start over here on the left. And what we have is we have two vessels, one on the left, one on the right. Think of them as glass, and think of this as the gas that we're talking about. And we have two molecules in the left-hand side container, one red one and one blue one. In the middle, we have stopcock, which initially is closed. And on the right-hand side, we have an empty second container, okay? If we open up that stopcock, there's four different arrangements those two molecules, the red and blue molecule, can have. And we're going to call each of those arrangements a microstate. And so let's take a look at what those are. So if we start on the top left here, we have a blue one on the left, a red one on the right. Then we go over one, now we have a red one on the left and a blue one on the right. We go below, we have that red and blue on the left, nothing on the right. And then finally we have nothing on the left and red and blue on the right. Those are the only four configurations that we can have for where those two molecules can be, okay, once we open that stopcock. So for this process, we would say there's four microstates because there's four different ways things can be arranged. So we could have predicted that through this equation. So 1/2 squared. The 1/2 means there's two places that the molecules can be. They can either be on the left-hand side or the right-hand side. There's no other choices. So two places can be, it's one of those two places they're at. And then the power, that squared, is the number of molecules. So for this example, we've got two places it can be, and we've got two molecules. So the math's actually pretty easy, pretty simple. We don't have a lot of choices here. It's 1/2 squared. And that tells us what are our possibilities. But do you remember Avogadro's number, 6.02 times 10 to the 23rd? Remember, we defined Avogadro's number as saying that tells us how many molecules of something are in a mole of that material. So let's say that we have a mole of stuff instead of just two molecules. Well, we still have this 1/2 value, right? Because there's still just two spots, left and right. But now that exponent, instead of being 2, is 6.02 times 10 to the 23rd. Wow. I mean, I didn't bother doing that on my calculator because I don't think I really need to. Because essentially what it's saying is it's 0. So the odds of it winding up with both of them on the one side is essentially 0, just when we're talking about 1 mole of something. 1 mole isn't very much. And so this was kind of the issue. And this guy named Boltzmann started doing math to figure out, well, how can I account for all these microstates that are going to be possible when we actually start talking about molecules and reactions and processes where you don't just have two places it can be and two molecules. So let's go back and take a look once again at this kind of gas example and just talk about gases again. So we look at the top figure. We have all of our gases at 1 atmosphere and the side, the pink side there labeled A. The right-hand side labeled B, nothing's there. Stopcock is closed. We open our stopcock, and what happens? The gas expands. This is our spontaneous process because we've said before that if you have gas and then you expose it to an empty container, it wants to diffuse into that. It wants to expand into that. And that's what we have here. We have this spontaneous process where half the gas now goes over to part B. And it's spread out uniformly throughout everything. And so now, instead of having one atmosphere on the left and nothing on the right, we have half an atmosphere on each side. So we're essentially have equal distribution of the gas because it's expanded throughout the whole volume that we have. If we go back to the final figure down at the bottom here, we see what would we have to do to get those gases out of B back into A? Well, that's not going to happen because it's not spontaneous. We could do it if, like before, we had a piston and we drove it or did something like that, but it's not spontaneous. And so these are the kind of things I started thinking about in terms of understanding it on more of a bigger scale. And this led Boltzmann and others to statistical thermodynamics. And so thermodynamics looks at the bulk properties of the substances. So in other words, the more macro, the bigger picture type thing. Because really, looking at it on a molecular scale is interesting, but it's hard to extrapolate that into these bigger systems. So this is where some of the math that they did came into play. And really, when you're talking about thermodynamics, it's statistics. And the key here is this word in parentheses, probability. What's the probability of things being in certain states and things being spontaneous and stuff like that? And if you remember last semester, we did some computer-based labs where we looked at electron densities and things like that. And remember, on those computer labs, we would get like these pretty pictures and parts of it would be darker and other parts would be lighter. And what we said was the darker parts, there is a higher likelihood in that case that the electrons were there. But what's similar to this is that we're talking about the probability of something. And that's what you're talking about in thermodynamics. If you go on and take more chemistry and get to physical chemistry class, then you'll do a lot of thermodynamics and thermodynamic calculations in that class. We're not going to get into that level of it here. We're just talking about the concepts behind it. But if you go on to PChem, then you'll do some of these calculations. I mentioned before the term microstate. And so a microstate is just the term we use for a single possible arrangement of position and kinetic energy of a molecule. Okay, we're going to have some examples of why that's important. Because what thermodynamics is trying to do is account for all of these different microstates. And as you'll see in a moment here, it's real easy to build up and have a lot of those microstates. They add up pretty quickly. So what Boltzmann said is there's a lot of these microstates. And you really can't look at every one of them. So he created a term called W, and that represents the number of microstates. And what he's saying is entropy is really a measure of how many of those microstates are associated with a particular macroscopic state. So you have this macroscopic state that you're observing. That's a sum of all the microstates that are in there. And he connected the microstates to the entropy of the system through this equation that we see, which is S entropy times K, which is the Boltzmann constant, this 1.38 times 10 to the minus 23rd joules per Kelvin value, and then the natural log of the number of microstates. So if you develop a thermodynamic law, you can name a constant after yourself. That's the takeaway here. So good luck. So entropy is really a measure of how many microstates you got. The more microstates you have, the more chaos you're going to have, the higher entropy you're going to have. And Boltzmann is looking to take the individual microstate type information, so that molecular level stuff, kind of bundle it together to figure out how entropy then is in the macroscopic state. Because the macroscopic at the end of the day is what you're most likely interested in. Okay, so we said previously that entropy is a state function. So that means that final value minus the initial value gives the overall change. Remember, state function, just interested in beginning and end. And that in this case, if you increase the number of microstates, then you're going to get a positive entropy change, right? So if the final is bigger than the initial, which is what you're talking about in entropy, because that's more disorder, more of those microstates, then you're going to have a positive entropy change. And so if we could rewrite that delta S expression, delta S equals K times the natural log of the number of microstates in the finals, minus that same expression times the natural log of number of microstates in initial. We can rearrange that a little bit and just get delta S equals that Boltzmann constant times the natural log of final over initial in terms of number of microstates. The key takeaway on this is entropy increases with the number of microstates in the system. And that makes sense because if our W final number increases, right, if that's a bigger number, then our delta S number is going to be bigger, just from our math equation here. But from a just expression, it's simply entropy increases as the number of microstates increase. Every one of those microstates, the way I think of it is, that's a little bit more chaos that you're adding. And entropy is a measure of chaos or randomness, things like that. So there are some things that can influence entropy, and two of the biggies are volume and temperature. So volume, particularly with gases, temperature most with everything. So with volume, we think of that as you get more microstates because the gas molecules can move around more, right? And so, since there's more places for the molecules to be, that's more microstates. More microstates means increased entropy. In terms of temperature, if we increase the temperature, then that increases the kinetic energy of the molecules, right? So those molecules are moving faster. As you get them moving faster, you have a wider range of molecular speeds. More molecular speeds means more kinetic energy values. That means you have more microstates. And as we've said a few times now, if you have more microstates, then you have increased entropy. So increased volume, more opportunity for those gas molecules to move around, increased entropy, increased chaos. Increased temperature, you got the molecules taking on more energy, they start moving around more, moving around faster, more chaos, more entropy. So increasing volume, increasing that temperature, those both increase the randomness of things. So up until now, we've been talking about kind of molecules just moving around in space or speed or things like that. But the interesting thing is that there's movement within the molecules themselves. And so I want to talk about some things that are called molecular motions. And the first one, translational motion, is what we've been kind of talking about. So that's where the whole molecule moves around. So if you think of yourself, you're in this room right now, if you started walking around the room, that would be translational motion, okay? But that's not the only motion you can do, right? You can do other motion. Let's talk about vibrational motion. And what vibrational motion means, it's the motion within the molecule, the atoms within the molecule moving. And let's look down at this figure at the bottom of the page. The three on the left are examples of vibrational motions. So in the molecules, and here we have a real simple molecule. We have a red atom and two white atoms attached to it. But if you look at the little arrows that are on these molecules, let's look at the first one on the left. We see double-sided arrow going from the white to the red on both of those. What I'd like you to do is think of that as a spring, okay? And if those two were attached by a spring, what could you do? You could have them going in and out, right? Back and forth. Well, that's actually what happens with molecules, is the atoms do kind of vibrate like that. The second one, we see another type of vibration. There, we see these two white ones kind of flapping back and forth. So think of it if you were standing still and you just started waving your arms up and down, okay? Flapping your arms. That's what's going on there. And then the third one is an example of where you see the white and red on the left kind of pulling out, the white and red on the right-hand side kind of pushing in. So going back to you, if you're the molecule, the translational motion would be you walking around the room. The vibrational motion, would you be flapping your arms or pumping your arms back and forth, things like that. So if you think about that, moving around the room, that gives you a bunch of microstates, right? All the different places you can be in the room. Now you're adding these vibrations, and here's a pretty simple molecule, 3-atom molecule. And there's other configurations you can have of these vibrations. That's just a few of them. But you've got that stuff going on. Each of those are a vibration, is a microstate, right? And now you've got these microstates on top of the translational microstates. You can see how this adds up pretty quickly. But wait, there's one more we want to talk about. Rotational. So what's rotational? It's just think of yourself if you stood there and you started spinning around. So in this case, you can see for the molecule, an example on the far right hand at the bottom, we have an imaginary axis coming down the middle of that red molecule, the red atom rather, and then it's just spinning around that axis. So that's another thing that can happen as well. So you can see you've got molecules moving around, that's the translational motion. You've got these vibrations within the molecule along those bonds. That's another type of motion that you have. And then you've got the spinning around. All of these things represent microstates. And so the other thing, and you probably figured this out already, but the more atoms you have, the more of these motions you're going to have, right? Here we just had 3 atoms. It's very common to have more than 3 atoms in a molecule, and now you've got all of them doing this stuff. It gets kind of crazy for a while. These vibrations that we see, these vibrational and rotational things, there's an area of chemistry called spectroscopy, and that's where a lot of these vibrations are known, what frequency or what wavelength they occur at, and you can actually do chemical measurements based on that kind of stuff. And so this vibrational stuff is pretty well known and pretty well documented about how to monitor it and use it to do analyses in that. But all of this stuff, the point here is, all of this stuff combines to where you see our initial example of the 2 little molecules with 4 different possibilities. Yeah, that wasn't too hard to understand and figure out. But gosh, you start adding all this other stuff and how many microstates you have, it's a lot. It's not something you're just going to say, oh yeah, I can estimate that in my head or something. And that was the whole beauty behind the thermodynamics that Boltzmann and other people figured out is how do you account for all this stuff to understand it? How do you account for it on this molecular level and then bundle it together, so to speak, to get you to understand how it happens on a macro level? So just to kind of review, if you increase the number of microstates, then you increase the entropy. Things that increase the microstates, that increase the entropy, include temperature and volume. So if you increase those things, it goes up. And if you increase the number of independently moving molecules. So if you have more molecules, you increase it as well. And then, of course, we know it increases with the size of the molecule, because then you have more of these vibrational and rotational movements that we talked about. So as far as I can tell, everything we do just makes it more complicated, makes it more chaotic. And for me personally, I think of that kind of like in my own life. The more stuff I do, the more chaotic it gets, the more complicated it gets. If I just do one thing a day, it's pretty easy. But if I do a bunch of things a day, a little more complicated. Same kind of with this thinking. So a while back, we talked about solids and some of the structure stuff associated with that. Well, entropy comes into play there, because if you think about it, when we talk about entropy, we're talking about how do things move in one fashion or another, right? And if we think of that movement, we know that there's the most movement in gases, a little less movement in liquids, and the least amount of movement in solids. Remember, that's what we talked about before, is we had those matrices, those solid matrices, things are kind of locked in, so to speak. And so it makes sense that the entropy of a system increases. It increases if gases form from either solids or liquids. It increases if liquids so liquids form from solids. And it increases when you have an increase in the number of gas molecules during a chemical reaction. So and that all makes sense, because it goes back to the second bullet point here of where the solids have the least amount of movement, the gases have the most. And that feeds into having more entropy, more chaos. So it is linked to the physical state. Okay. One last thing I want to talk about before we end here. And that is, let's just do an example here, which kind of highlights the entropy in the physical states. So the top figure that we have here shows how water entropy increases as you go from solid to liquid. And I think that makes sense to us probably, but let's go over it anyway. So on the left-hand side here, we have frozen water, and we're going to have this rigid crystalline structure, right? And so what that means is those molecules aren't moving around. So we've lost that kind of microstate, because it's just sitting there, it's stuck. It's not going to spin around because it's frozen, it's stuck. The only thing we really have left is the vibrations. So we still have the bonding, that movement associated with the bonding, but that's it. So in terms of our choices of microstates, it's relatively few compared to now we go to the liquid. So the liquid, we still have that vibration that we talked about with the bonds, the spring bond type concept. It can spin around a little bit, so we have that rotational, and it can move around the liquid a little bit. So we do have some of that translation motion going. So we have a little bit more number of microstates because we added some other things. Well, then we get to the gas phase of water, and we get even more. Because we still have the vibrational and the rotational that we had in liquid. But now we've got so much space there that we've got free movement of the molecules. So we don't have any of this thing like in the liquid where maybe they run into each other or they get stuck or something like that. Here now is full movement. So that just gives you a visual on how you see that progression of the microstates increasing. And because of that, the randomness, the entropy increasing as well. Then at the bottom, we have an example of where we have 2 moles of NO plus 1 mole of O2. So that's 3 moles of gas. Well, those react to form 2 moles of NO2. So here on the left-hand side, we had 3 moles of gas. Now on the right side, we have 2 moles of gas. Having fewer moles of gas decreases the entropy because there's just fewer pieces, is the way I think of it. And so because you have less stuff, less moles, less molecules, however you want to think of it, in that right-hand side, you're going to get less entropy from that because you've taken 3 and combined them into 2, basically. Okay, so the next thing is third law of thermodynamics. We'll work on that on Thursday. Just to remind everyone that next Tuesday, we will have a quiz on this stuff on chapter 19. And I'll see you Thursday to finish up the thermodynamics. Any questions before we leave? Okay, thank you.
Yeah.